Here's a photo of our team all together, starting from back left to front right. We have Nathan Wolf, an electrical and computer engineering student, Ian Shaw, a mechanical engineering student, Stephen Perry, our procurement lead and a mechanical engineering student, Austin Davis, a mechanical engineering student, Eric Lawson, an electrical and computer engineering student, and finally myself, Jesus Serrano, an industrial engineering student and team lead. And together we make up Team 22008, also known as Team 3-Putt.
Our team has been given the opportunity to work with Ping, which is a professional golf equipment manufacturing company, to develop a mechanical putter performance pendulum. The goal of our project is to design and create a system that repeatedly mimics a human swinging a putter without the swing parameters changing from swing to swing. These variable parameters include changes in the X, Y, and Z axes, as well as 2 adjustments in the pitch axis and 1 adjustment in the yaw axis. Once the parameters are set to their desired locations by the operator, the swing can then be executed. Upon completion, the system will reside in the Ping Putter Lab that is primarily used for monitoring and analyzing the putter swing of humans. This even includes PGA pros. With our system, Ping will use it to test new putter head developments and then analyze the results for further developments in the competitive game of golf.
There are a number of requirements which our system must comply with, such as it interfacing with the existing Ping testing lab, it being electrically powered, and being overall safe to operate. However, our mission-critical requirements were those pertaining to the system's functionality, such as its mobility, the existence and length of its setup routine, the ability to swing it putter, and the ability to adjust the axes.
The putter system consists of 3 primary mechanical subassemblies. This includes the frame subassembly, the motor mount and linear gantry subassembly, as well as the swing arm subassembly. Beginning with the frame subassembly, this consists of 40/40 aluminum extrusions which have been cut down to size, as well as brackets which are used to hold the 40/40 extrusions together. Additionally, there is a top shelf which houses the motor mount system, as well as a bottom shelf which houses the system electronics. Finally, there are also 4 wheels located on the frame subassembly which are used to lift the system and allow it to be easily maneuvered from one position to another. Next, there is the swing arm subassembly. This system consists of custom designed components and allows for the Y-axis adjustment as well as the yaw adjustment of the putter angle using a custom 3D printed worm gear system, as well as the pitch adjustment which may be made using a custom designed elbow system. There is also a putter clamp, which ensures that the putter is held securely in place during testing. Finally, we have the motor mount subassembly, which consists of 2 linear gantries which are controlled via encoders and may allow the user to make computer adjustments that are accurate down to 1/1000th of an inch, as well as 2 elbows on either side of the motor mount which allow for the motor swing axis to be adjusted from 0 to 20 degrees of inclination in 5-degree increments through the use of quick-release pins. The motor mount subassembly mounts to the top of the frame, and the swing arm subassembly then mounts to the rotating arm of the electronic motor.
Moving into design changes for the mechanical putter pendulum, our entire system has gone through numerous revisions over the semester. Starting with the frame subassembly, the previous connection between the top and middle faceplate and the 40/40 extruded aluminum utilized 3-way corner bracket connectors, but now these connections are mated by 90-degree brackets. During transportation, the 3-way connectors experience an abundance of shear stress, causing one corner to break. The 90-degree brackets mitigate this shear stress, allowing greater strength between these mates. For our motor subassembly, our design previously consisted of 3 6061 alloy machine parts which would ultimately house the motor, offer inclination of the motor, and properly mount to the X-axis linear guide rail. This subassembly is now comprised of 8 separate parts connected by 1032 threaded screws. 3 machine parts was not feasible for machining purposes, so splitting the motor subassembly into 8 separate parts would reduce wasted material and cost. Additionally, the original design incorporated motor inclination between the top and bottom, motor mounting plates mated by machined holes on both plates, and a 7-inch pivot pin. Now our design includes the top and bottom motor mount plates being mated by a purchase hinge due to the old design requiring much more machining to create the holes for the pivot pin. Located towards the middle of the swing arm subassembly are original cast iron worm gear weighed approximately 10 pounds. To decrease the load on the motor shaft, the design now incorporates a skeletonized 3D printed worm gear made from ASA material, which significantly decreases its total weight. The original putter grip was designed to slot and hold the club shaft by U-bolts. In order to mitigate grip movement and possible damage to our sponsor's property, our final design consists of a top and bottom plate mated through purchased T-handles.
Once the system is connected to the computer, the user shall calibrate the X and Z axis motors using the homing routines on the software. The system shall set the position of the closed loop stepper motors using the hard stops on the linear guide rails. These guide rails can be set to a desired position using the software for precise movements or the handheld pendant with the labeled momentary switches. After that, the main axis for the swing arm is commutated and calibrated for the position of the swing arm. The user can also adjust this position of the swing arm using momentary switches on the handheld pendant. Once the calibrations of all three motors are finished, the user will insert a putter into the putter clamp and tighten the 4 T-bolts to hold the putter in place. After securing the putter to the swing arm, the setup routine is complete. The system consists of 2 different modes for swinging the putter. The first mode is a force-driven swing, where the user can enter the drawback angle of the putter in the software. Once the swing is executed, the putter will draw back to the user-defined angle relative to the starting position, then follow through on the swing until it reaches that same user-defined angle on the follow-through swing, then finally return back to its starting position. The second mode for this system is a gravity-fed swing. Once again, the user will enter the desired drawback angle in the software. Once the swing is executed, the putter will draw back to that specified angle, then the motor will be disabled, allowing it to freely rotate, and the putter will fall due to gravity.
Our initial design for the mobility was to have a handle on the left side of our system along with 2 wheels on the opposite 2 legs. The user would lift up these handles and tilt the unit and allow it to roll on the 2 wheels. After further inspection, our unit was quite heavy, so we decided to implement a wheel on each leg that has an engagement and disengagement mechanism to lift the unit up off the floor about a ½ inch so that you can roll it around like a cart. This is how our system rolls much more easily with one user. For our safety, we have chamfered every edge of our aluminum. Anything machined has been filed down so that there are no sharp edges and no risk of a user getting cut walking past the device. We have also implemented an emergency stop on our user control pendant, which they can hit and cut power to the entire system, as well as a hand switch that you can smack on the top surface of our unit. There is also a warning light that will engage and start blinking red whenever the system is active.
And finally, we'd like to give a special thank you to our sponsors Truman Louth, Kurt Pauley, and Tom Trueblood, our class mentor Wee Lee, and Ping for letting us do this project.